In this video I'm going to introduce you to the start of complex numbers, which is something that we've talked about quite a few times, but now we're actually going to look at how to use them and what they actually are, and then we'll go on to lots of different things, how they can come in very handy when we're solving more complicated problems and how they open up lots of new options for us. So we're used to solving quadratic equations of this form where we have real coefficients, so a, b and c are real numbers. And we know we can use the quadratic formula to solve these, and we've talked quite a lot as well, and you'll be talking about this in your normal maths course, about this, which is the discriminant, and how important this and how much this tells us about the particular quadratic, depending on whether it's positive, equal to 0, or negative. So we should know by now that if this is positive, so if it's bigger than 0, then our quadratic has two real distinct solutions. Okay, we solve plenty of things like this, where you can factorize it maybe, you get your x values, 2x values, or you can use the formula, get your 2x values, but we can square root something that's bigger than 0, nice and easy. Square root 25, you get 5. Okay, and we get the plus or minus, so we'd get plus or minus 5, which would give us the two separate solutions. Okay, we should also know that b squared minus 4ac, if that's equal to 0, then we get one real repeated root. So if you factorize it, you get the same. Remember, solutions can be interchanged with the word roots, so solutions, roots are the same thing. So if b squared minus 4ac is equal to 0, we get one real repeated solution. Okay, so for example, if you end up factorizing and you get this, then you get x is 4 repeated. That's because the quadratic that you had, if you work out the discriminant of this, you'll get the discriminant to be equal to 0. If you don't believe me, then you can try it, but it will work, and if that happens, you get repeated roots. The one thing we should have talked about, is the last option, where b squared minus 4ac is less than 0, and we get 0 real roots, or 0 real solutions, if this is the case, because we can't square root a negative number. Okay, well, so far up to this point, we've not been able to square root a negative number. Okay, but we can extend our number system to include a value for the square root of minus 1. If we can imagine that there's negative numbers, like you can count physical things like 1 pen, 2 pens. Can't really imagine minus 1 pens or minus 2 pens, but we can appreciate how you get negative numbers. So why can't we appreciate how you can square root a negative number, perhaps? But that introduces a whole kind of new ball game, because we know when we square something, we always end up with something positive, so how can we square something and get something negative? So we call this square root of minus 1. Rather than calling it a value or a particular number, we're going to call it I, which is an imaginary number. And we're going to start using this in lots of different ways. Okay, so I is the square root of minus 1. This means we can have lots of different imaginary numbers, like 4i, or 7i, or minus 3i. Anything with an I in is an imaginary number. And if we've got a real part as well, like this, then we call this a complex number. So a complex number has two parts. It has what we call the real part, which we're going to highlight in red, and it also has an imaginary part, which is in green. And together they make this complex number. Okay, so these are imaginary numbers, these are complex numbers. And in reality, a real number, like 3, is just a complex number where the imaginary part is 0. So obviously we wouldn't never write that, we just write 3, but a real number just means the imaginary part is 0. But this is how we use I, and this is what complex numbers are. Okay, because of the way this sets up, because I is the square root of minus 1, root minus 1 is going to be very, very useful in lots of our questions that we're going to look at, and also all the laws of surds that you've learned. So the root of AB, I know the notes are all over the place at the moment, but you've got proper notes written down, so this is just to kind of to talk about it. We can split this into root A times root B. So for example, root 50 is root 25 root 2, so we get 5 root 2 to simplify it. Okay, in exactly the same way, we can do the same with imaginary numbers. Okay, and that's what question 1 goes into. So if you in your notes, if you look at question 1, so there's a few little notes for you, and then question 1, we're going to go straight in now and look at these. So let's write each of the following in terms of I, so the square root of minus 36. So when we've got a negative sign under the square root, we're always going to take out the square root of minus 1, because we know that's I and we can replace that. And using our laws of surds, we can put this as root 36 times root minus 1. Okay, we can do this with any number, it doesn't matter what it is, minus 42. You can change this into root 42 times root minus 1, because the 1 doesn't change the value, but the minus 1 will change the sign. So we always want to be thinking like this whenever we're trying to simplify these imaginary numbers, or write them in a slightly different way. So we're always trying to get root minus 1 out of it, because then we can put I in. Root 36 is 6, so this is just 6 times root minus 1, which is I. So root minus 36 can just be written as 6I, using those laws of surds, just like root 50 can be written like this. Root minus 36, if we take out that root minus 1, then we get our real part kind of here, root 36, and we can split it into two things. Okay, root minus 28 is the second one. So similar idea, root 28, root minus 1, and the more you get used to this, the more you can just kind of, hopefully when you've done this loads, which you will do, because you'll want to practice loads, this bit just becomes kind of self-explanatory. So you know as soon as you see the minus in the root, you know that there's going to be something I, or root 28I in this case. And again, we'd always simplify surds if we can. So root 28, you want square numbers that go into that. So 4, so root 4, root 7, root minus 1, we've changed it to I. So it's just 2 root 7I. And just be careful where you write your root sign. You can put brackets around this if you want to make the I obvious. I just tend to, as you know, if I've taught you, make sure this doesn't, because if you write something like this, then the I is under the square root, which is wrong. So I would make it really clear that your square root ends, and there's a clear kind of gap, so that you know yourself that they're separate, and also the examiner knows that they're separate too. But this is basically laws of surds with this added option of root minus 1. So that's question 1. Let's have a look at 2. So complex numbers can be added or subtracted by adding or subtracting their real parts and adding or subtracting their imaginary parts. And we can also multiply in the usual way as well. So let's have a look at 2a. So we've got 2 plus 5i, excuse me, plus 7 plus 3i. So in order to add our imaginary or our complex numbers together, we take the real parts, so 2 plus 7 is 9, so you add the real parts together, and you take your imaginary parts, 5i and 3i, and you add them together, and you get 8i. So basically, all that algebra that we've done, that's coming in handy here. Okay, that's exactly how it works. Okay, so year 8 should really be able to do that without them knowing what I is, but obviously we've got a secret meaning of I here. We know that I represents the square root of minus 1. B, same kind of idea. 2 minus 5i minus 5 minus 11i. So 2 minus 5. If you want, you could kind of expand the second bracket to make sure. Oops, I put pi in there by mistake. What was it? 11. So this is 2 minus 5i minus 5 plus 11i. So 2 minus 5 is minus 3, and then minus 5i plus 11i is plus 6i. So this should be nice and straightforward for us. Trust me, it does get a lot more complicated, but for now, we just ensure we can't assume that these things work in the same way, but certain things we can. Once you've been told that they work in the same way, or you can prove that they work in the same way, then you can use those facts. Okay, so 2 lots of this. Again, I'm going to do 2 times 5, 2 times minus 8, exactly as if I was expanding the bracket as a year 8. And then finally 10 plus 6i divided by 2. Same kind of idea. I can write this as 10 over 2 because they're both over 2. I could think of it like this. Again, I probably would leave that step out at this stage. 10 divided by 2 is 5. 6 over 2 is 3. So I get 5 plus 3i. And a couple more questions. So we'll look at 3 and 4. So 3a is 4 minus 2i over root 2. So we can rationalize denominators just like we can do when it's not complex. So here we can times the top and bottom by root 2. So we'll get 4 times root 2 on the top, minus 2i times root 2, so minus 2 root 2i. And the bottom I'll get root 2 times root 2, which is just 2. And I can simplify, 2 is common here. So 4 root 2 over 2 is 2 root 2. And minus 2 root 2 over 2 is just minus root 2. And then we're just going to have the I tagging along as well. So again, hopefully nothing new here. Excuse me. And then 2 minus 6i over 1 plus root 3. Again, remember when we rationalize the denominator here, we flip the sign in the middle of our surd here. 1 plus root 3 will times top and bottom by 1 minus root 3. And again, this is like expanding a bracket on the top. You can imagine you've got brackets around this, can't you? I'm going through this quickly because I'm hoping we're confident doing this, and if we're not, we need to get really confident, otherwise we're going to be struggling. So 2 times 1 is 2. 2 times minus root 3 is minus 2 root 3. Minus 6i times 1, minus 6i. So we're just doing this whole business here. And minus 6i times minus root 3 is plus 6 root 3i. Okay, so all our laws of algebra carry on. 1 times 1, we can get minus root 3 plus root 3, and then root 3 times root 3 is 3, so we'll get minus 3. These cancel, so we're still rationalizing. And we can simplify the top. When you have these complex numbers like this, you want to keep all the real parts together and all the imaginary parts together. So in this, my real parts are 2 minus 2 root 3. And my imaginary parts are minus 6i plus 6 root 3. So they're already together, but if they were jumbled up, we want to keep all the i's on the right, all the non-i's on the left. 1 minus 3 minus 2, and then simplify. Again, minus 2 goes into everything here. So 2 over minus 2 is minus 1. Minus 2 root 3 over minus 2 is plus root 3. Minus 6i over minus 2 is plus 3i. And plus 6 root 3 over minus 2 is minus 3 root 3i. And if you wanted to be extra clever here, and this comes in handy, you might take the I out as a factor. We tend to write it second. And in fact, 3 is common here too, isn't it? So we'd have 3, 1 minus root 3i. That gives us 3i, and minus 3 root 3i. So it all checks out. So we can factorize here as well. And then the last question, question 4, or certainly the last part in this little section anyway, we've got z1 is 4 plus I, z2 is 7 minus 3i, so they just give us 2 different complex numbers which we tend to denote by z, and 1 and 2 the subscripts just to distinguish between the two. z1 minus z2 is just this one minus this one. Remember to put it in a bracket because it's got 2 bits. Expand the bracket, 7 minus 4, so we get this. Part B is 4z2, just 4 lots of this, and then we can just expand. So again, this is just more practice of the same thing. And then part C, 2z1 plus 5 z2, so 2 times z1 plus 5 times z2, and again, all our bid mass, everything like that, 2 times 4, 2 times I, 5 times 7, 5 times minus 3i. Real bits altogether, 8 plus 35 is 43. 2i minus 59 is minus 39. So that should be a nice kind of gentle introduction to complex numbers. The first bit just explaining what's going on, what complex numbers are and where they come from, why we use them. And the next bit is all really quite straightforward stuff, but just getting used to seeing I a lot and using I, and making sure it just highlights how good we've got to be with our algebraic skills, like expanding brackets, negative signs, rationalizing denominators, squaring out brackets are going to come into play, all those kind of things, solving equations. We've got to be really good at all these things.